Welcome again to our third discussion session. And we start today with Bob. We'll follow up on the second lecture of Matthias today. Go ahead, Bob.
All right. Thank you. So last time I had some slideshow and, I discussed some of the parts of the lecture that were a bit, or things that couldn't really be discussed in the lecture. And I had a similar thing planned for today, but I think at the last minute, I decided that it might be better to talk about things that came up as questions and that people seem to be a bit confused about. So in particular, one thing that I'm not sure that not everyone here is completely comfortable with is sort of vertex operators in string theory and how this relates to states and how you define these things. And this is going to be a very important part going forward in the talk when you talk about correlation functions. So I thought it best to take some time, maybe 15 minutes or so to talk about that. And then we'll get back to our scheduled programming of trying to answer questions or have a discussion about the lecture. So first, let's just talk a bit about vertex operators. So vertex operators are a very essential ingredient in doing any computation in string theory. And the basic idea is that you start with some state, psi, let's say, and there's a correspondence between that state and some local operator, which we'll call v psi, and it's local on the world sheet. And there's a correspondence between these two, which has been touched on in Madalena's lectures as well. So the essential way in which this works is that if you take the state v psi of z and you act on, say, the vacuum of the CFT, so the unique state which is invariant under all of the global symmetries, and then you take z to 0. So in most cases, you can do this limit without any problem, and you just get some operator located at 0 acting on the ground state, and this defines for you a state. And due to the way that conformal symmetry works, you can also go backwards, but for now, let's just say you have an operator, it defines a state. So in our specific worldsheet example, so in our example, so on ADS3, the worldsheet theory has states which look like M1, M2, potentially spectrally flowed, which we talked about today. And dual to these states, there are going to be vertex operators. Which depend locally on the world sheet. Now, one important part of what we're going to have to do going forward is to understand the operator product expansion of, say, our free fields, psi plus and minus and eta plus and minus, with these vertex operators. So with v m1, m2, w of z. And on the new problem sheet, you'll actually compute this yourself. But let me just demonstrate how this works for w equal to 0. So when you're unflowed. And let's just stick with the psi modes because the eta modes are going to be almost identical. So recall that psi 0 plus acting on the state m1, m2, this is just the same state with the value of m2 shifted up by a half. And then because this is a highest weight state, psi plus annihilates the state for all modes which are bigger than 0, so greater than or equal to 1. And similarly, you can write down the same expressions for psi 0, and instead of shifting m2 up by 1, you shift m1 down by a half. potentially with a minus sign. And you have the same condition that Xi minus annihilates the state for all of its positive modes. So you can turn this information into an OPE between Xi plus and minus and the vertex operators. And the basic way you can do this is to first start by giving, say, Xi plus some Z dependence and seeing how that as a function of Z acts on the state. So there's a mode expansion that we can use. So we break up Xi into some modes. Each mode has a factor of minus Z to the minus 1/2. The 1/2 because Xi has conformal dimension 1/2. And acting on the state M1, M2. Now, because of this, because of the fact that M1, M2 is highest weight, this gets rid of a lot of the terms in the sum. So what you're left with is Z to the minus 1/2, Xi plus 0, acting on M1, M2. And then sum over N, and I'll change the sign on N just to make things a bit more clear, of the negative modes acting on M1, M2. This term in particular, this is O of Z to the 1/2. So typically when we talk about an OPE, we forget things that are regular as Z goes to 0, because we typically only care about the divergent parts. And so this is just Z to the minus 1/2 Xi, M1, M2 plus 1/2. And then plus things that are regular. So now we can upgrade this into an OPE between the vertex operators and the free boson field. So we can rewrite this first line as being Xi plus of Z and V M1, M2, 0 spectral flow, acting on the vacuum state. This is at 0, acting on the vacuum state. And then we can also write this line in terms of vertex operators. So this is Z to the minus 1/2, V of M1, M2 plus 1/2, 0, at 0 times the vacuum state plus things of order Z to the 1/2. And so from this, you can just read off the OPE. This is Z to the minus 1/2, V M1, M2 plus 1/2, 0. And then plus things that are of order Z to the 1/2. And then you can just shift the values of the coordinates. So you can shift this coordinate and this coordinate. And so for two general points, say Z and zeta, you get something that looks like this. So you have Z minus zeta to the minus 1/2, V M1, M2 plus 1/2, 0 of zeta plus things that go like Z minus zeta to the 1/2. And that's essentially how you can read off the OPE between these two operators. And you can do the same thing for the minus Xi boson, and you can do the same thing for the eta plus and minus. And in particular, you can work out what happens at non-zero spectral flow. And essentially what's going to happen is the degree of this divergence here is going to change. So for the psi plus term, I believe, you'll end up with something that looks like this. So it's going to be z minus zeta, but now to the minus w plus 1 over 2. And then the same structure here. So now, let me also talk a little bit about the X basis, which Matthias brought up today, but might need some more clarification. So as Matthias mentioned, you want to find a correspondence between correlation functions of operators in the dual CFT, so in the symmetric orbifold theory, and you want this to be equal to some integral over some moduli space of some correlation functions of vertex operators on the string theory. The problem is that naively, these vertex operators have no dependence on the X variable in the dual CFT. And so we need to find a way to introduce it. And the way you can do this is as follows. So given a vertex operator on the world sheet, for instance, if I wanted to translate it, so I want to consider the vertex operator at z plus zeta, then this is basically v of z sandwiched by L minus 1 modes in the exponentials. The way to think about this is that purely classically, in terms of conformal transformations, L minus 1 generates d by dz. So this is the translation operator. So just like in standard quantum field theory, where you translate operators by sandwiching them with exponentials of the momentum operator, here you sandwich with exponentials of the L minus 1 mode of the Virasoro algebra. And so you can do the same thing for the X component. So there's a holographic dictionary, which was briefly mentioned, but let me mention it again, which essentially says that you map the 0 mode of J plus to L minus 1 in the dual CFT. The J3 0 mode gets mapped to L0 of the dual CFT, and the J minus 0 mode gets mapped to L1 of the dual CFT. And the motivation for this essentially is that the 0 modes, plus or minus 0 and J3 0, these satisfy an SL2 algebra, which is the same algebra as global conformal transformations on the sphere, or Mobius transformations, which are generated by L minus 1, L0, and L1. And so through this holographic dictionary, you can find what the translation operator is in the dual CFT, and it's J plus 0. So given some vertex operator, you can define what its X position is, or how to shift it to have an X position, as simply being e to the x J plus 0 v of z0 e to the minus x J plus 0. And if you need an interpretation of such an operator, then consider the following cartoon. So we consider AdS as a cylinder, or you can consider it as a solid ball, but a cylinder is a little more common. And the boundary of AdS3 is where you want your dual CFT to live. And this essentially is conformally equivalent to the two-sphere. And it has some points on it, say X. But then you also have a world sheet propagating within AdS3. So you have some world sheet that, say, maybe radiates from X and then scatters around, does whatever the world sheet does. Maybe it has some non-trivial topology. And the point at which the string is emitted, that is Z. Yes, I see a raised hand. Go ahead.
Sorry, Bob, I have a question. I'm confused why the boundary of AdS3 is 2 instead of the cylinder.
The cylinder and the two-sphere are the same conformal geometry. So for instance, you can map the cylinder to the two-sphere through the exponential map. So you can think of the two-sphere as basically being the complex plane with a point in infinity added.
Oh, okay, thanks.
Yeah, so you have concentric circles, and these essentially define concentric circles along the boundary. This is 0, this is infinity. Yeah, so that's basically how you introduce the X dependence onto the vertex operators, which is going to be a very important concept going forward in the talks. So that's essentially all I had planned to talk about. So now I can just open to discussion and questions about anything.
Right, are there any questions? So let me ask the, oh.
Yeah, no, I mean, I also had a very naive question. So,
Okay.
Matthias, we mentioned the construction of the spectral flow, and then you sort of you shift slant a little bit the spectrum of the theory. He has this
Yes.
map between L naught, and so you get some negative L naught eigenstates after you shift it. Should I be worried that I mean, these states they have they have negative norm.
Yeah, so that the energy on the world sheet is somehow bounded below or something, or is not bounded below, or.
Well, I mean, I know that there is something funny happening with the way. I mean, in the end of the day, you have some cohomology of states, and you're just taking some slice out of this states you construct. I'm not just sure exactly how that works, because I mean, if you have negative L naught states, then the descendants will be negative norm. So this is not a unitary spectrum, but somehow, I mean, I know that since the construction works, then the states, they must somehow be not a BRST invariant. So
yeah,
how does that work?
Let me just try to comment on that best I can. So basically the spectrum before you spectral flow. So let's say we're in some representation. So you can look at the L0 eigenstates and the J30 eigenstates, and they're gonna make some grid. So they might be misaligned or something, but you know, you have some grid of states, and let's assume that I'm brave enough to draw all of them. Now, once you spectral flow, so let's say I have a state MJ or something. Once I spectral flow, the energy of, say, MJ spectrally flowed W, well, it'll have a J30 eigenvalue of M plus KW over 2, but let's pick K equal to 1 for now. And they'll have some L0 eigenvalue, which is the original L0, so I'll call it delta 0. It's some function of the J's, and whatnot, minus mw minus w squared over 4. I believe that's the expression you would get. So if you take this state, it has these eigenvalues. So now if I consider the same representation, but now I've spectrally flowed everything, I end up with some similar graph, except now I have a bit of a slant to it. So it looks something like this. And so I think this is the graph you were, or this is roughly the picture you had in mind. So for any fixed value of, or basically the L0 eigenvalues are going to be unbounded from below. But whenever you take the physical state condition on the world sheet, you're going to take L0 is equal to 0. Normally you'd expect L0 equal to 1, but this is one funny part about the hybrid formalism, is that the appropriate physical state condition is to take L0 equal to 0. Some funny thing that comes out of topologically twisting everything. And so when I take L0 equal to 0, so maybe I have some L0 component coming from the T4, then that's just going to pick out some slice here. Any slice. So maybe this one, maybe one negative one, depends on what's going on in the T4. And so once you pick that slice, everything is fine. And in particular, one of the nice things here is that the J3 spectrum, which represents the spectrum of the dual CFT, is bounded from below. Does that answer your question?
Yeah, just I mean, I guess that if you try to construct some descendant of these negative L naught states, will they also get I mean, projected out by the physical condition?
I believe it depends on what's going on in the T4. So for instance, I could take some descendant of this L naught state and say, you know, move up, but if I appropriately move down in the T4, then I can counteract that.
Oh, okay.
Yeah. So this is, for instance, what when Matthias was talking about how you have some states with some negative oscillators, some dimension. You have, say, this state on the T4 in the dual CFT. I guess, let me be more explicit here. If you try to take this state in AdS3, then you can look at the level matching condition here, and whatever level matching condition you do for the AdS state has to be counteracted by the level coming from the T4.
Right. I mean, I just have a quick follow-up. There's a question by Lucas, but just too good opportunity to pass. You can sort of do the same thing with the Virasoro algebra itself, right? Instead of having some current that, I mean, the usual thing is that the highest weight state, they have this J plus of the whatever current you have, they will annihilate the state, and then you construct the states with J minus. Then you begin the construction by assuming that the sum of the J pluses, they don't actually annihilate the state, then you have this shifted. But you could do that in principle with the Virasoro algebra itself. Consider a state where you don't, I mean, you're not annihilated by L1, but you may annihilate it by L2. Well, this is a global SL to see, so it's not too different. But let's suppose that you have a state in the CFT where you are annihilated by L2, but not by, well, actually, by all Ln's with n greater than or equal to 3. So
Sure.
In the way that's not just global, the global vacuum, it's something. Does this work the same way? Do you know any reference behind this, or am I just?
So if you just took some standard 2D CFT, so not a string theory, but just some 2D CFT, and you tried to consider representations of this form, that I do not know.
Okay.
Yeah. It sounds a little weird, but I don't know.
Yeah,
maybe you
it
can
seems
even start thinking of finite dimensional representations and just, you know, rotating.
I mean,
because rotation of the picture is just taking a different basis of generators. I'm not
Right,
sure it
but
will
you
work in the
need, but you
final answer.
need, but you need a current algebra for this to make sense, right? Well, I mean, I can just work it out myself. It seems a bit like this Whittaker state modules that people consider in CFT. I don't know.
Okay.
Okay, so, thank
Yeah,
you a
that
lot
I know
for
nothing
that.
about, but
Uh-huh.
yeah.
Yeah, there's a question
yeah.
from Lucas in the chat.
Yeah,
his
let me look at
microphone's
it.
not working. Okay.
So why does the Lagrange multiplier for the U1 constraint have no moduli? If I understand correctly, you are only integrating over complex structure, which comes from the Lagrange multipliers of the force zero. I'm not sure I fully understand the question.
Well, this is something
But
about.
okay, I think I actually know where this is going. So whenever you implement, say, the diffeomorphism constraint on the world sheet. So let's say you have diffeomorphism invariance on the world sheet, and then you try to gauge fix it, you end up with some ghosts. So you end up with maybe like a BC ghost system. And whenever you introduce this BC ghost system, the correct interpretation in the path integral is to integrate. So you have to integrate over zero modes. Zero modes of B. And this integration is what leads to the integration over the string moduli space when you're, say, calculating any correlation function. And so I think the question that's being asked is why you don't have a similar moduli space to integrate over when you gauge out the extra U1. And the answer is you do. So typically you do have an extra set of ghosts. So if you were to try to implement this U1 fixing from the point of view of the world sheet, you would end up with a ghost system that needs to be integrated over. This doesn't really matter for the sphere. I think there's some subtlety about conformal killing vectors or something analogous to this, but this isn't really a problem on the sphere. But as soon as you try to do anything at higher genus, you find that you do need to integrate over some extra moduli that exactly come from this U1 gauge fixing. So yes, very good question.
Okay, more questions?
Yes,
there's
Cynthia.
a question from Cynthia.
So could you give a more like maybe high level explanation of the spectral flow like diagram you draw there? So what was like a more like general effect of the spectral flow here?
So I'm not entirely sure what you means by some high level explanation.
Like for example, you just had this diagram and then this like before the flow, you could have this J0 go from negative infinity to infinity.
Yes.
J30, and then after the spectral flow, you could have a like highest weight. What is that? So
basically, how do I get from this picture to this picture?
No, like so after having this highest weight, what is the significance of this?
The significance is that, I mean, maybe I'm interpreting the question wrong, but the significance is that sort of exactly what I was talking about with Bruno's question. So once you pick out some physical state condition, so say taking L0 equal to 0, then essentially what that does is it picks up some L0 value on the ADS. And the resulting set here, this resulting highest weight set of states, this corresponds to the spectrum in the dual CFT. So it's actually good that after spectrally flowing, we end up with some, for each value of L0, you end up with some lowest weight representation of the J3 or of the SL2R zero mode algebra, because that's sort of interpreted as the spectrum in the dual CFT, which you want to sort of be bounded from below.
So basically, if you don't have the spectral flow, it wouldn't work like your duality here. Is that what?
Yes.
Okay.
Yes. And in particular, you could really say that there aren't any interesting states at zero spectral flow that survive the mass shell condition. So there's essentially one state that contributes to the spectrum of the dual field theory in the zero spectral flow sector, and that's just the vacuum state. And the reason for this, if you want to think from a different perspective, is that spectral flow, W, this corresponds to cycle length of W in the dual CFT. So in general, you have some cycle, which looks like to W, but there's no such thing as a zero cycle length permutation. I mean, even the trivial permutation is just built of a bunch of cycle length 1 permutations. And so really there shouldn't be anything interesting happening at spectral flow equal to 0, and indeed there isn't.
So are you saying basically without the twist in the T4, like you wouldn't basically have you only have a more like a trivial state there, is that?
Yeah, so if you try to take W equal to 0, what you find in terms of the dual CFT is that that's basically just the vacuum state. That's just the identity operator.
I see, thank you.
Of course. And so from this point of view, W equal to 1 sort of corresponds to, this corresponds to untwisted states, or the untwisted sector in the dual CFT, because a permutation with the only non-trivial cycle being length 1 is just the trivial permutation. And so really you should think of W equal to 1 spectral flow as being sort of the lowest amount of spectral flow that you should consider in your world sheet theory.
More questions? I wanted to ask a very naive question. How do you see N in the world sheet picture?
Which N?
Big N, which is would be Sn, the rank of the permutation group in the dual picture.
So the only way that you can really see N, I mean, in the end, we're really taking N to infinity. But the way that N is going to appear is that when you consider some correlation function, let's say we're in the dual CFT. So it's some correlation function. This is going to have a genus expansion. So it's going to have a sum over all genera greater than or equal to 0. And I believe it gets weighted as 1 minus G minus N over 2. And in this sense, you take G string to be 1 over the square root of N. Because if you do this, this corresponds to the standard string perturbation expansion, where you take G string to the Euler characteristic or something. And this is really the only way that you can see N from the world sheet theory. So on the sphere, N doesn't appear anywhere. The only effect that taking N to infinity has is that you can consider cycle lengths of any size. But when you start doing higher order corrections, N will appear through the size of G string. In particular, I don't think anyone really has any idea how this works when N isn't infinite.
So my maybe confusion was that on the CFT side, well, yeah, you do have the scaling of correlators, and which means that it forces you to take different covering surfaces, right? When you're computing. Oh no, maybe not. Maybe it's W that defines which kind of covering surface you take.
Yes, W determines, so
the genus, right?
Yes, so the W's themselves determine the covering surface. I mean, for any set of W's, you will have multiple covering surfaces, also of different genera, but you'll have a finite number.
Okay, good.
In particular, for any set of W's, there's a maximum genus, which is allowed.
Right. But that is not seen in the string theory picture, right?
It is.
Okay.
So in particular, if you try to calculate the perturbative expansion of any of these correlation functions, it truncates, which is a very interesting property of this worldsheet theory.
Even though it is kind of infinite.
Infinite in what sense?
Well, n is infinite, so you should see this.
Yes, yes.
So yeah, I don't know if this will be discussed at some point.
Potentially, I don't know if Matthias is planning to talk about the truncation of the spectrum, but basically I can outline the idea, which is that for a given, and maybe I'll talk a bit more about this tomorrow when I plan to talk a lot more about these covering maps. So for a given W1 to Wn, so I'm considering fields of twist W1 up to Wn, there's a finite number of covering maps that have these critical points for any fixed values of X. And there's a maximum genus. So there's a maximum genus that occurs. And so that means when you take the string perturbation theory, the sum is over G less than or equal to G max. So the perturbative expansion is finite. But I think that's something we don't fully understand the implications of yet.
Interesting. So there's a question from Lucas, one more question from Lucas.
Oh, yes, I wasn't looking at the chat. Is taking spectral flow equivalent to a topological twist? No, I don't believe so. So what you're saying is like taking spectral flow here seems to be taking L0 and then adding some J contribution, which looks a lot like a topological twist that people might consider in, say, topological string theory, where you take the stress energy tensor and relate it to the tensor plus del J. And as far as I know, these two have no relationship to each other, other than looking somewhat similar because you have, what I think, L0, if you spectrally flow, Ln goes to, now let me think about just L0. So L0 goes to L0 minus W J03 minus W squared over 4. So I don't think this has anything to do with topological twisting, but it does look suggestive. I agree. Of course.
All right, I think we have time for maybe 1 or 2 questions.
Great.
Anyone wants to make one? Do you know if this story is how much the story changes if we move from T4 to, for example, S3 cross S1? That is.
You've asked our great shameful secret. So S3 cross S1 is a theory that is, anytime it gets a chance to be annoying, it is. So in particular, there is a free field realization for ADS3 cross S3 cross S3 cross S1, which essentially looks like one pair of these bosons. So instead of having xi's and etas, you just have a xi and a xi plus and a xi minus, and they have some commutation relation. And then you also have some fermions, I think. they have similar commutation relations. And you can work out the spectrum of strings on ADS 3 cross S, 3 cross S, 3 cross S1 if you pick a particular choice of radii for the S3s using this free field realization. But so far in trying to calculate, say, correlation functions, we've sort of been at a loss. So this is something we don't understand yet. But
is there similar shortening condition in this case?
I believe so, yes. Yeah, so instead of having, say, representations of PSU 112 at level 1, you have representations of D21 alpha, which is some other supergroup that is exceptional and has some weird properties, such as having a continuous parameter, which is something you don't see very often in the algebras. But so I believe in terms of the representation theory here, there is a shortening condition, although I'm not entirely sure on that. Because the S3 cross S1 story is something I'm not super familiar with.
Why I'm asking is, so I have a confusion about the shortening versus, let's say, supergravity picture. So there's a paper of Matthias with Lawrence and other collaborators where they compute the spectrum in the supergravity. And it looks like a discrete spectrum, right? So
yeah,
but since it's not a small k, I suppose, or is it for fixed k? I thought, well, it cannot be because it's a gravity picture, right? You'd not expect.
Yeah, I vaguely know things about this paper, but not to any detailed extent. But yeah, so there was this old claim that claimed to compute the spectrum of strings on ADS 3 cross S, 3 cross S, 3 cross S1. And then I think this paper showed them that those considerations were wrong and that you end up with some discrete spectrum. But I think there was some tensionless limit taken there, but I'm not entirely sure.
Okay, thank you very much, Bob. Very interesting discussion. Now we have to go to the next discussion by Clay in a couple of minutes or two.